Gas absorption in aluminum castings. Hydrogen is the only gas that is appreciably soluble in aluminum and its alloys. Its solubility varies directly with temperature and the square root of pressure. During the cooling and solidification of molten aluminum, dissolved hydrogen in excess of the extremely low solid solubility may precipitate in molecular form, resulting in the formation of primary and or secondary voids like pinholes or gas porosity. Fluxing and flushing of aluminum melts are practiced mainly for two purposes as listed below. First one, to prepare molten aluminum metal from the aluminum oxide dross layer. Second one, to remove dissolved hydrogen and entrapped dross from the melt. In the flushing method, as also discussed, inert gases like chlorine, nitrogen, helium, or argon gas is simply piped from storage tanks through graphite tubes directly into the liquid metal. The piping of inert gas creates bubbles which move upwards, and the hydrogen gas dissolved in aluminum melt migrates readily to the bubble where it collects and is flushed from the melt onto the atmosphere. Draw separation by fluxing is due to the mechanical action of the inert gas bubbles carrying oxides to the surface. Fluxing means adding suitable agents in order to achieve the following. First one, to react with the dross so that it can float up. Second one, to prevent reaction of the melt of aluminium with atmosphere by acting as a barrier. And third one, to absorb impurities in the melt. All aluminium alloys in general are melted under flux cover of halide salts. These fluxes contain salt mixtures that are liquid at normal aluminum melting temperatures. Typical fluxes are A 47.5% sodium chloride, 47.5% potassium chloride, and 5% sodium aluminum fluoride, or B 45% calcium chloride, 45% sodium chloride, and 10% sodium fluoride. Other cover flux combinations include aluminum and zinc chlorides. Some manufacturers of cover flux recommend that the flux should be stirred in the melt to be effective so that the dross can be easily separated from the metal. Most oxides are of aluminum, but alloying elements such as magnesium, iron, copper, and titanium also can form their oxides. Grain refinement in aluminum castings. Grain size in an aluminum alloy refers to size of individual aluminum crystals in the solidified part. The size of these crystals is directly related to the number of grains or nuclei found during the initial stages of solidification or during pouring of metal. The more the number of grains, the finer the grain size will be, thereon having the ability to promote improved casting soundness by minimizing shrinkage, hot cracking, and hydrogen porosity. Also, the mechanical properties are greatly enhanced with fine grain structure. Grain size in aluminum alloys can be refined by the following three methods. First one, thermal method. Thermal method involves rapid cooling, chilling of liquid metal, and subsequently variation of process variables. A fine equiacid grain structure arises when casting is carried out in cold molds and under and under low superheating conditions. Chemical method Chemical methods involve the addition of some elements called grain refiners that promote nucleation and hindering crystal growth. Inoculation is a typical example of this method and is the most common practice by adding aluminum, titanium, carbon, ternary master alloys to the liquid metal before casting. These particles act as aluminum grains, resulting in a uniformly fine equiacid grain structure in aluminum castings. Mechanical method. Mechanical refining method involves stirring or agitation of the melt during solidification by using ultrasonic, electromagnetic, and mechanical stirring methods. Since most of the techniques require long processing time and special devices, this method is usually applied to semi solid metal processing.